Okay, are we good to go? Yep, good. Right, good afternoon. I'm Ben Dukes. I work for a company called CodeThink, but that's not really important for this presentation. I'm going to go through a little bit about some old computer system that I used to have, and presentation here. I'm going to be releasing this all under CC by SA4. The slides and everything else will be put up on a GitHub account hopefully before I return home. We'll get the Brexit joke in first. I'm wearing black because I am in mourning for our country's extremely stupid decision. I'm just hoping that I'm going to get through this presentation without losing my voice, because I haven't been very well. No, I haven't been to China recently. So the first thing, a little bit of history. Now, I don't know if anybody else knows about the VIC-20. It's a lesser-known brother of the Commodore 64. I think it was released around the 1980s, so even I was young at that point. It had 20 kilobytes of ROM, 5.5 kilobytes of RAM. I've listed out a half on this, and that was about $299 when it was released. I think that's about 700 or 800 euros nowadays. So it wasn't exactly cheap for selling that thing. Anyway, it was one of the first computers I had. Obviously, I didn't get it new. I got mine secondhand because I really, I wasn't not quite that old. Anyway. And the second thing is that I came across, did a bit of nostalgia searching across the internet a year or so ago, and I came across a 16K RAM expansion. Now, that pretty much filled out your system RAM, and I would have loved to have one of these when I was much younger. I had, I think, a 3 kilobyte RAM expansion. I really loved that, because whilst it says 5.5K of RAM, about 3 kilobytes of that is available to the user for programming by default. The rest is used by the screen and the operating system. So there wasn't really much chance for writing your own code, and because of the limitations, a lot of the games would come on ROM cartridges, which you would fit in to the slot, which was like this edge connector, which I'm assuming most people are familiar with. So, why does this talk exist? Well, as I said earlier, this was my second ever computer, and I was browsing around this board, and I came across this upgrade, and I was thinking, do I have enough information from this to work out how it worked? Because I was actually slightly interested in what was going on. I thought this was actually simple, and I'm going to go through some of the technology involved in the next few slides, which might explain to people who don't know about the details of the hardware what was going on. So there's two types of RAM from this sort of era. There's the static and dynamic RAM. So nowadays there's pretty much now dynamic, because that's the stuff that's won. But in this space, most of the expansions use the static RAM. And this one, from looking at the picture, was using dynamic RAM. And I was thinking, that circuit looks a bit too simple. And I'll go through. So, as I say, two types of the RAM. So dynamic RAM was a bit faster, but it comes with a couple of downsides. The address bus is multiplex, so you have to give it address in two parts. Whereas SRAM just had a standard address bus, you just gave it an address and a read and write. Dynamic RAM requires a refresh. So in this case it's 128 rows, requires every single row to be accessed within a 4 millisecond window. Otherwise, the contents of the RAM will start decaying. Now, the bit here that I think made the DRAM more interesting to manufacturers is it was actually cheaper. Now, I haven't got exact prices from this point in time, but it's about 4 or 5 times cheaper to go with the DRAM. And when you're talking about what was about $50 or $60 worth of memory, spending that money on making it simpler, but adding extra components around it, was worth it. I say this is sort of a state machine of how you go about a DRAM access. I'll explain a bit more about that. But this is a bit more complicated than simple logic decode that was used on static RAM. So the VIC-20 has a rear expansion port, which is where this cartridge plugs in. It's a really simple extension of the 6502 CPU main bus. As I say, it brings out the 8 data lines and 13 of the 16 address. You get the read and write. There's some pre-decoded chip selects because they'd already done some of the work for you of working out which areas were being accessed. A CPU clock, which was running at about 1 megahertz. It varied slightly depending whether you had a PAL or NTSC version because they used the video reference to divide down for the CPU reference clock because they were trying to make a very cheap machine. And there's a few other things like a soft and a hard interrupt. Now, unlike the Z80, the 6502 doesn't have an inbuilt refresh. At least with the Z80, there was actually some help for building DRAM-based systems where they had a CPU refresh in there. But it's a basic parallel bus in this diagram. I mean, this is a simplified timing diagram. You get an address set up during the low cycle of the clock. You get some data roughly in the high cycle. And by the time it's ended, it's expected the data to be valid for read or it's been written for the write. Now, as I say, it's about 1 megahertz in this, so we're about talking about 1,000 nanoseconds for a cycle. And going with how the DRAM would work is that you start with the row address of the row you want, and that's sampled roughly on the active edge of the RAS signal. Column address is again on the active edge of the column address, and then at some point pretty soon after you either read or write the data. And again, just below this is a refresh cycle where all you need to do is just give the DRAM the row address. So that's a little bit of an introduction about how the DRAM works. So let's go back to what I was thinking when I saw the picture. So I'm thinking, actually, there's probably enough information from just looking at the picture to tell me roughly what's going on. I say it's all pretty much standard logic gates. We're not talking any sort of FPGA type stuff. That wasn't available back then. The best you'd find is programmable logic arrays that were fairly simple. You're talking and or gates, probably 14 cells. And we're talking, there's definitely no PLL in this because if you're doing a state machine, you often, for modern FPGA, would require a PLL to get your 8 or 16 times clock. And there's definitely no room for that. That's just a quick list of what there is there. I'm not going to go through it too much. There is a counter, so I'm thinking that the first point, the counter is probably the refresh counter. So I've already got some clue as to what's going on. And there's some MUX chips that select one of two inputs. So I'm thinking, wonderfully drawn diagram. Probably the address is coming in. The first MUX would probably select whether I'm taking the row or the column. And there's probably another select for what I'm doing for the refresh, and that gets presented to the DRAM. Now, I'm still not sure how on earth they're actually working out when they can refresh, because usually you would hold off an access, do your refresh, you can then let the processor back. So I was reading through the data sheets, and then I came to a realization. The refresh cycle is only 400 nanoseconds. I have a 500 nanosecond inactive window on the bus cycle because it's not faster, it's not the fastest 6402 you could get. You could just refresh when it's not doing an access. This would simplify the state machine. I mean, the problem with that is that you're going to use a bit more power, but when each of the two DRAM chips that are on the board are drawing 26 milliamps in refresh, and a normal VIC-20 is drawing about 16 watts of power anyway, the designers are not really caring too much about the power. So I've driven a new state machine, so I'm now working out that there's a probably clock high for an access, clock low, do a refresh. That will simplify my thing. Now I'm just going to skip. I drew up some schematics thinking, this is now a thought experiment for me. So, I mean, what would I do next? You know, I could just leave this alone. No, I go on eBay. So the first start of this madness is that I actually buy one. I find one on eBay. I spend about 30 euros, take it out of its cartridge, and I'll show you later, I've got it here. And I take photo. And this is the first stage of actually a full reverse engineering of this sort of thing. I've got a photo of this, and I've got a photo of the underside of the board now. So pretty much, unfortunately, you can't really see on this projector, but you've got two DRAM chips, the counter, there's got the state, the 2-to-1 muxes for the address, and some logic. So I can use that to look at the board. I can use a multimeter to check whether a pin is connected to another pin or not. Fairly obviously the power pins are all connected. But what do I also see? There's actually, but hidden behind the capacitor that was in the picture here, there's another capacitor. There's actually more capacitors than I thought. Now, coming back to the fact of state machines, actually, resistors and capacitors make a fairly good delay. If you've done electronics, you can use them to make delays. So I can actually do a state machine by a series of delays. So I'm fairly sure that actually this is going to work quite nicely. And I've got a really good idea now how this works. I can actually draw a schematic. And I can use the tools I have to actually trace out and verify what I've done. So this is the underside of the board, and this is the next part of the technique of reverse engineering, is that I can draw, so I can flip it over, I can draw with marker on it saying what everything is, the edge connector, and actually work out definitely how it is all connected. So I've actually gone a step further now. So I actually used Eagle for this. I'm very sorry, it's not an open source product. I had a few problems getting my Eagle to KiCad conversion working that I've been working on. I will actually be moving to this. So I drew it out. I had a board, I've had 5 boards made, and it actually works. I was quite impressed at that. You can very much, if you can just see down there, there is a piece of bodge wire. Somehow I missed the CPU read and write line, which is just fairly blooming obviously. Now I would have brought my VIC-20 along with me, but unfortunately I don't have a power supply for European plugs, and I wasn't sure how easy it was to get through customs. So anyway, So I've actually built this, and it does work as standard. So I'm quite amazed that something that simple can actually make a very good implementation of a state machine. Now, it works fairly well because the VIC-20 is slower. If it had been faster, you couldn't have got the refresh into the inactive part of the cycle. So I was almost right on my first go. I mean, if I'd had that extra component, I'd have probably got the initial circuit right. But as I say, I've got the refresh. Thank you. I say I'm probably going to actually get through my time slot a little bit faster than I intended, because I forgot that my original presentation actually had a demo in it. So, as I might have said, going back to a little earlier statement, I know that this board works. Now, I ended up actually buying 2 VIC-20s to go with this. So this little adventure in reverse engineering, which started out as a thought experiment, has ended up actually costing me about €100 of money in buying parts, because of course the first one turned up and didn't work. So I got another one to get the other one working. So I've gone through some of the techniques I did use. Now, I had an actual thought of, which would have actually saved me some time and money in the long term. I could have actually just simulated this. I was actually so intent on actually building a physical implementation that I forgot that simulators exist. Now, back when I started, you'd pay good money for something which would do this, but this is actually a open, not sure if it's open source directly, but this is Circuit.js, and you just put your circuit in here and you can put stuff in and it will just show you a waveform, and it's like, yep, that worked. So that was the thought which would save me some time. So, I mean, going forwards, I might try and optimize the design, but I think it's actually, with the amount of components there, it's fairly optimal already. Now, I was thinking that, I said earlier that PLLs weren't really around. Now, there were some chips that you could use for a PLL, and you could probably actually build a very simple logic-based state machine. Whether that's worth doing or not is another point of, am I wasting my time on this? So, to sort of wrap up this presentation, I'm putting the project files for the PCB, the presentation, the simulation, and the other little things I've used to produce the presentation. I'm going to put those up on a GitHub, which I've put URL I put there. I say there's some very nice stuff like the waveforms have all been done in WaveDrom, which is another way of just taking some text and producing a nice diagram out of it. And at that point, thank you very much all for attending. Now, I think I've got plenty of time for questions, for about 10 minutes.
Hi, you've taken a really honest approach to reverse engineering. Have you considered taking a USB logic analyzer for a few euros and just clip it on the lines while the machine is running, so then you could just have a nice look at the...
The question is about putting a USB logic analyzer on the machine and using that to work out what's going on. Now, I did think about that, but that would have required me to have upfront bought the machine, which I wasn't intending on doing in the first place. This was basically I found this one evening and I thought, well, that looks simple. How is this working? So yes, nowadays a simple logic analyzer would have probably given me the same thing. I could have probably got a lot of information out of attaching a logic analyzer to the real thing and actually looking at it. But as soon as you got that, it's fairly easy with these sort of systems to actually just trace it because it's 2-layer PCBs. You don't have anything really hidden within the board. Whereas a lot of complex modern systems, you might have 6, 8, 10 layers, and once a signal vanishes into the board, you've lost it. So.
Yeah, the Vixen board is a switchable 16K RAM
Yep.
module. I saw you replace the original switches for the 3K or 8K or 16K RAM with jumpers.
Yes.
Could you please, maybe if we have time enough, elaborate a bit more? How is this
So,
selection scheme working, and
rough-
why is the 3K?
Okay, so there's a couple of questions here. Firstly, about how this the module that I've chosen has a certain amount of selection for the memory, and that there's where it says it's a 16K, there's a 3K module mode. So the first easy bit is I couldn't get the switches, so I just used jumper headers to replace them. Now the memory map of the VIC-20 already has 5 kilobytes of memory in it. There's 2 8K selectable areas, and the jumper has just changed which of the chip select lines are fed into the logic of the Vixen. So depending on which one you select, you may just end up overlapping an original 8K section. However, some of the original programs you get would assume you'd extend that extra 3 kilobytes because that's part of what you could get. And some of the really small expansions were simply 3 1K SRAMs that would sit there. So that's why there's an option. So basically, the 16 kilobytes is 2 8K blocks, and some of that, depending on which way the switches are selected, could overlap an existing RAM area.
Yeah. Okay.
So at the back there.
Yeah. So the original card has RC type, RC resistor capacitor
Yeah.
and Smith trigger
Yeah.
for implementing the states.
Yeah.
And you proposed we can use an PLL to multiply the clock and some shift registers.
Yeah.
Did you think about a technology that was used in between simple RC logic and the PLL and shift registers? There are in the dip form factor delay line chips where you put a pulse in and get the same pulse like 50 nanoseconds,
Right.
100 nanoseconds, 150, and so on, like 5 taps on an LC thing with Schmidt triggers integrated in one chip. Did you think about that?
No. So the question was, there's a technology like between the simple RC and a PLL using a delay line. Now, I didn't actually think about using delay lines because I haven't actually come across those very much in any of the standard computing stuff. So I think delay lines are technology I've not seen used. So I don't know about, but it's a very interesting idea. It's like how there are a number of ways of doing this and which one would have been possible or cost effective. So
I've seen those delay lines on different PC compatible mainboards and memory expansion cards, so from between 85 and 95.
okay, so yes, so the comment is that these have been used on a certain PC expansion and motherboards between like the 85 95. Now that is about the time frame we are talking about. I can't remember exactly when this cartridge was first put in. I think the copyright on mine was 82, and I have actually brought something to show people. So here is the original. It's boxed. And this is what we're looking at. Now, I was trying to get some of the values of the components on here, and I've actually destroyed one of the capacitors in doing it, so it's actually got a replacement on there. It turns out that, so it's,
Yeah, what value?
so I think that was a 3.3 nanofarad, I think. So but yeah, these boards are not exactly easy to deal with. because they're not actually very desperately well made, and they certainly don't have any nice features like solder masks. But anyway, that was, I can show people that close up if they want to look at it later. I say this has got a slightly different switch on it. I say, and this is the one I actually built. I say, I don't know why on earth I ended up with 5 of them. So.
Why only 16K? Why get more? 4K,
Yes. So, I mean, the question is why only 16 kilobytes? So, I mean, I was just recreating this pretty much chip for chip. These are 16K by 4 DRAM chips. So I'd need more chips to get more memory. If I put 32 kilobytes on the expansion, I'd fill pretty much the entire spare memory map of the VIC-20. Anything more, and I'm looking into having to do memory paging, and that is getting to the point of there's probably even weirder ways that I could build memory expansions at this point. And this way is getting to the point that is probably not worth my time.
Probably.
Yeah, I'm just curious. You said the VIC-20 was your second computer. What was your first?
So, okay, so the question is that the VIC-20 was my second. So I had a ZX81 as my first. And if anybody remembers the ZX81, that had even worse RAM expansions, because those would actually fall off the back of the computer. So the VIC-20 at least had a proper case. So yeah, this. I mean, this is probably I probably spent about 10, 12 days of my time from last year on this. And I don't know whether this is really a good use of my time. It certainly made an interesting talk, I hope.
You got 2 VIC-20s out of it. So.
Well, yeah, I've actually repaired. So the comment was I've got 2 VIC-20s out of this. Now, one VIC-20 was probably one VIC-20 more than I needed. I've actually repaired the second one as well, because I could probably sell that back on.
Well done.
It turned out the VIC chip on it had died, so that was why I wasn't getting anything out of it. But that was another evening of, why on earth is this not working? And there was a sidetrack of probing through, finding out what was wrong. And the fact that China still sells VIC-20 chips. So.
Didn't you have any problems getting the old memory chips nowadays?
So, question is, did I have any problems getting any of the old chips? Now, it turns out that eBay is a fount of all knowledge or supplies on this, and there are people still selling these DRAM chips. I think it cost me about €3 for a pack of €3 each for a pack of 4. I say there's still people with stocks of these things sitting around.
Same date code.
I don't know if they've got the same date code. This is an 84, 45.
Do they both of them say have same date code?
All of the chips are the same.
Original and that one.
So so the question was, do both the DRAM chips have the same date code? And yes, actually they do.
They are fake.
Probably fake, yeah. Who knows?
Yeah.
I mean, who cares? It works. But
They rub ink out of it and make the same date code, because those are not making for 20 or 30 years. So there is no way there is all stock anymore.
well, it could be, because it is actually the date code is 84. So that's 19. That's 9. Yeah. But yeah, the comment was that it could be, the stock could well be fake. Who knows? It works.
There was a lot of military installations in Russia
Yeah.
that had big stocks of these memories and stuff like
I
that.
mean,
And they are selling them out.
yeah. I mean, so I think the question, I don't know if it's going to be reliable or not, but I mean, as I say, AliExpress on China is still selling the video interface chip that's used in the center of the VIC as new old stock. And I was quite surprised. It's like you just go online, order it, and a month later a chip turns up. Anyway, well, hopefully this was interesting to people. Thank you for attending. You're welcome.